So this is a quick recap of the matrix multiplication algorithm that we saw in the lecture. So what kind of algorithms are we seeing? So let's say we are given two matrices, say n by n. A and B, right? And A is written as A ij and B is written as Bij. The elements are Aij's and Bij's, right? Let us also fix the notation for the product. M is equal to A times B, which is, let's say, Mij. Okay, I and j are indices which run from 1 to n. Okay, so here I, j are indices which take values in the set 1 to n. Right? So the first is a very elementary algorithm, right? So the first is elementary algorithm using the definition. Right? What is that? So let's call this, I think we call this math multi in the lecture. So the inputs are the two matrices, right? So we have start stop. What do we have? So we first need to create the matrix M, which we need to return. Right? So create M equal to Mij, right? So create an N by N matrix, M equal to Mij. There will be some values initialized. That doesn't matter. We could say all Mij's are 0 initially. It really doesn't matter. Okay. What else do we do now? So once this is done, in the next step, now we have to run through all i's and all j's, right? So we need two loops, one for each variable. So for I equal to 1 to n, and then for the next variable also for j equal to 1 to n. Okay. And now we have to store the sum that comes out of multiplying the ith row with the jth column. That is what we have to do. So the sum, I had initialized it as a variable s equal to 0, but we don't really need to do that. Instead, we can just take Mij equal to 0. Let me initialize it that way. That's the initial value for Mij. And now we will range across the index of the components when we multiply the ith row of A with the jth column of B. So when k ranges from 1 to n, we simply add the sum. So Mij, whatever was initially, it gets added with the value A ik times B kj. Okay, so the star is the notation for multiplication. Right? So initially Mij starts with the value 0. Then as k ranges from 1 to n, you keep on forming these products Aik times Bkj and adding them to Mij again and again and again. So at the end, when k has run through 1 to n, the element Mij, right, the variable Mij has the value of the full sum, all possible terms Aik times Bkj as k varies. The sum of all those terms will be stored in Mij. Right? So that completes this for loop. And that is it. So Mij for a fixed value I and j is this value. There is nothing more to be done. Right? So the for loops all end. Okay, all three for loops end. When all three for loops end, for j as well as I, all the Mij's are now ready. So we just now have to return the matrix M. That's all, because M contains these values M, I, j. Right? So that was a basic elementary algorithm using the definition. Right? And what else did we see? Well, sorry. About the runtime, what we saw is that each Mij takes time order n square. Sorry, order n to compute. Since there are how many products? N products and n sums to compute. Right? Do you see this product and this sum happens again and again and again for each value of k from 1 to n. So there are n many such operations, n many products and n many additions. So each Mij takes time order n to compute since there are n products and n sums. Further, there are total n square terms Mij since I and j are varying from 1 to n, right? Therefore, the total runtime is, what is it going to be? N squared into order n. That is what it is, which is equal to order n cube. Okay, so that is it, runtime. All right, so this was the algorithm. Now the second thing that we saw was by block multiplication. Okay, but this is again a simple block multiplication. Okay, so now let's give this another name. So let's call this block multi. Again, the inputs are the two matrices A and B, right? And now we have start and stop. And now we start. So here, so go back to the lecture that we just saw, okay, lecture video, and note that, okay, so I write it anyways here. We consider the block decomposition A equal to, so there are 4 matrices, right? A11, A12, right? So let me write A21, A2, right? Similarly for other matrices. Okay, this is the notation where each of these blocks is an n by 2 cross n by 2 matrix. Okay, so further, where each smaller block is an n by 2 cross n by 2 matrix, right? That is what we have. Therefore, what do we get? So how do we compute this? Now it's much simpler, right? So we obviously create the n by n matrix m equal to Mij. That is done. This is the first step. But the second step, what we need to do is we also need to create this block partitioning. That is also very easy. Okay. Block partitioning is almost obvious, but we need to pass that as a command when we write down an algorithm. So create the block decomposition for which all matrices for each of them. Okay. Block decomposition. So let's write it for A. Okay, this is the first command. Let's put full stops. That's better. Since these are words, let's put full stops. So create the block decomposition A. What else? You repeat this. Create a similar block decomposition for B. What does it mean to say create block decomposition? It means create these smaller matrices, right? Create the n by 2 cross n by 2 matrices. That is what it means. Okay. And then you have these. Create these n by 2 cross n by 2 smaller matrices and give them these names. That is the meaning of creating a block decomposition. So now these are ready. Okay. Now what do we have to do? Now there isn't much. Now just feed in the formula that we already know, right? So we have M11 is equal to A11 times B11 plus A12 times B21, right? Similarly, the remaining blocks. So M12. So go on checking if this is fine or not. Times B12 plus B12 times. Then the second row of blocks is A21 B11 and then the last block into 2 A21 times B12 plus A22 times B2, right? This is not just the formula, this is the actual commands that you give in the algorithm. And this completes the computation of M11, M12, M21, M23. Therefore, this block decomposition has been computed. And now one simply needs to do return M. That's it. The block multiplication command algorithm is done. That's all. All right. And what did we see here about runtime? So about runtime, so we saw that if Tn is the runtime for, let's say, block multi for n cross n, then we have the recurrence that we have is Tn is equal to, so then we have the recurrence as we saw in the lecture. So if this is not clear, just go back to the lecture and check. Okay, 8 times Tn by 2 plus theta n square. Why is 8? Because the smaller, so again, this matrix multiplication, A11, A12, these multiplications are done using block multi for the smaller ones. Okay, so now you get the idea where the recursion is coming. There is a small mistake here, the way I wrote it. We are supposed to use recursion. Okay, so the recursion step comes here. I'm not writing A11 times B11. I'm saying block multi A11 B11 plus block multi A12. Is that okay? This is the recursive step. Okay. So now can I repeat this everywhere? Yeah, I can repeat this. Okay. I am supposed to repeat this. Block multi. Okay. Recursion for the remaining ones also in the same way. Okay, now it's complete. Right? This brings us to another thing. If we are doing recursion, what is the base case? Base case is n, right? N equal to 1. Base case is n equal to 1. So once again, we need to add a few lines for the base case. So if n equal to 1, what do we do? Then we simply return, then the only element is a11, little a11. Okay, so then we simply return little a11 times little b11. That's it. Else we have all of this. So I'll indent them also properly. Okay, and then accordingly there is an ended. Is that okay? So this completes cycle. Why did we do this? Because the formula says multiply the smaller blocks, but we want to multiply the smaller blocks by using recursion, by inductive argument, right? We want to use the same function for smaller blocks. Okay. Therefore, for smaller blocks, but then when we go inside, there is a base case. Base case is n equal to 1. When n is equal to 1, the matrix A is just the value A11. Matrix B is just the value B1. So the product is just this product scalar, nothing else. All right. So that is what this is. And therefore, this, how many times are you using the smaller block multi? There are 1, 2, 3, 4, 5, 6, 7, 8 times, which is why you have this 8 times P of n by 2. Plus theta n square is for all these additions as we just saw before. Okay. And then solving these recurrences gives us again P of n is equal to theta n cube. You can use master method or some such method and then get theta n cube. Okay. So where are we right now? This block multiplication algorithm, which gives us runtime theta n cube, is roughly the same time as the previous elementary algorithm that is also running in order n cube, right? So the mat multi and block multi are basically having the same runtime. Okay, block multi is not better yet. But now we'll see that if you do block multi in a slightly more careful manner, then we can make it better. Okay, that is the whole point of this lecture, so to speak. Okay, so what is the improvement? That is called Strassen's algorithm. Okay, so let me write it clearly. Faster algorithm, and that is called Strassen's algorithm. Okay, it's given by a person called Strassen. So what do we give this name? Let's call this Strassen multi. Okay, again, inputs are A and B. We have start and stop, and we begin. How do we begin? Well, the block multiplication part is the same, right? We have to create the same block multiplication. So we will copy this thing. So again, the initial part is same. If n equal to 1, all of this part is the same. Okay. So these block decompositions have been created and, oh, sorry, the base case was not written. Create the matrix, and then we have this. Okay, so this part is just the same as what we did before. Base case and creating the block decompositions. The second part is where we now have the change, right? So we create these smaller parts. So what parts do we create? So we create these functions R1 A, which is defined to be the row sum of the first row, right? So A11 plus A12, R2 A, row sum of the second row, A21 plus A22. Let's do this for B also. We need this for B as well. Okay. So R1 B is equal to B11 . Now we have to write this separately for each of these because we cannot simply say to, in an algorithm similarly do this, right? That's the problem. So we have to define this separately. What else do we have? We have C1A, but now it's column wise difference. Okay, A11 minus A21, C2A equal to A12 minus A22. Similarly for B, B11 minus B21 and C2B. Second column difference, B12 minus B2. Second block difference. So the row sums are done, the column differences are done. What else now? The diagonals, right? So DA is equal to A11 plus A22 and DB equal to B11 plus B2. These are the definitions that we required. Okay. Once we add these, okay, now each of these is basically a sum or a difference. So each of these could be computed in theta and square many operations because these are all n by 2 cross n by 2 matrices, right? And now comes the interesting part. The smaller block multiplication. Earlier we did 8 block multiplications. Now we only need to do 7 block multiplications, right? So that's it. So now those P matrices that we saw. The P is, so now just as I mentioned before, it's block multi. We are using block multiplication for smaller size matrices for n by 2 cross n by 2 matrices. Okay, block multi A11 and C2B. This was the first definition. P2 is let's say R1 A and P3 is block multi of R2A and B11. P4 is block multi A22 and C1B minus of block multi. There is a sign change in P4. P5 is block multi of the diagonals. So D of A and D of B. Okay. P6 is the column times row. So block multi of C2A with R2B. And P7 is symmetric gradient. So block multi of C1A with R1B. I think in the lecture I mentioned R1A, so that's a correction. It's R1B. Is that okay? That's it. So how many block multis have we used here? We have used block multis of n by 2 cross n by 2 matrices 7 times, not 8 times, only 7 times. That will make all the difference. Okay. Further now, how do we get the blocks? So now the formulas are M11 is, so I'm just copying P4 plus P5 plus P6 minus P2. M12 is P1 plus P2. M21 is P3 plus P4, and M22 is P1 plus P5 minus P3 minus. Okay. Now these are again additions and subtractions, so these can be done in theta and square time. Therefore, so now we are done with the whole matrix M, right? So now we just have to return M. That's all. And then we'll just end the if that we have. So, all right. So this is Strassen's algorithm that we just saw. Okay. And now, what is the remark on the runtime? So now there are only 7 block multis used, right? So for the runtime, let's call it again T of n. We now have the recurrence. What is the recurrence now? T of n is equal to 7 times T of n by 2 plus theta n square. Okay, and solving the recurrence. So you can try to solve this using master method or any other method that you find okay with. So solving this is T of n is equal to theta, not n cube, but n to the log, I'm sorry, n to the log 7. Okay, but log 7 is less than log 8, which is equal to 3. Okay, therefore this is strictly less than n cube. So this is little o n. In fact, it is little o n to the 2.9 even. This is because this is close to 2.8. Okay, so this is quicker. Therefore, Strassen multi is faster than block multi. Okay, that is the main result. All right, so yeah, that was a quick recall of what we did today, and I'll stop it here. Okay, thanks.